Hello and welcome. In this video, we will explore a powerful technique for integration known as integration by parts. This method is a key component of the IB mathematics analysis and approaches higher-level curriculum. By the end of this session, you will be able to derive the integration by parts formula from the product rule of differentiation, apply the formula to integrate products of functions, and solve more complex integrals that require multiple applications of the formula. Let's begin by understanding the foundation of this method. Integration by parts is a direct consequence of the product rule for differentiation. Let's recall the product rule. If we have two differentiable functions, u and v, the derivative of their product, u times v, is equal to u prime times v plus u times v prime. Now let's integrate both sides of this equation with respect to x. Integrating the derivative of u times v gives us u times vi. On the right side, we integrate the sum of the two terms. Our goal is to find a way to integrate a product of functions. Let's rearrange this equation to isolate one of the integrals. If we subtract the integral of u prime v from both sides, we get the integration by parts formula. The integral of u times v prime dx is equal to u times v minus the integral of u prime v d. This formula is the core of the method. It allows us to transform a potentially difficult integral, the integral of uv prime, into another integral, the integral of u prime v, which we hope is easier to solve. A common alternative notation is to let do equal u prime dx and dv equal v prime dx. This gives us the formula in a more compact form. The integral of u dv equals uv minus the integral of v do. The key to using this method successfully is choosing the right parts for u and dv. A good rule of thumb is to choose dv as the part of the integrand that is easy to integrate, and u as the part that simplifies when differentiated. Let's apply this to our first example. We want to find the integral of x times e to the power of negative x. Our objective is to find the integral of xe to the power of negative x dx. First, we need to choose our u and dv. We have two functions multiplied together, x and e to the power of negative x. Let's try setting u equal to x and dv equal to e to the power of negative x dx. Now we need to find do by differentiating u and v by integrating dv. The derivative of u equals x is do equals dx. The integral of dv equals e to the power of negative x dx is v equals negative e to the power of negative x. Now we have all the components for our formula, u, v, and do. Let's substitute them into the integration by parts formula. The integral of u dv is equal to u times v, which is x times negative e to the power of negative x, minus the integral of v do, which is negative e to the power of negative x times dx. Let's simplify this expression. This simplifies to negative xe to the power of negative x, plus the integral of e to the power of negative x dx. The new integral, the integral of e to the power of negative x, is much simpler than our original integral. We can solve it directly. The integral of e to the power of negative x is negative e to the power of negative x. So our final answer is negative x e to the power of negative x, minus e to the power of negative x, plus the constant of integration, c. We can factor out negative e to the power of negative x for a cleaner result. This gives us negative e to the power of negative x times the quantity x plus 1 plus c. To verify our answer, we can differentiate it using the product rule and check if we get back our original integrand. The derivative of our answer is e to the power of negative x times x plus 1 minus e to the power of negative x. This simplifies to xe to the power of negative x, which is exactly what we started with. This confirms our solution is correct. Let's try another example. This time, we'll find the integral of x times cosine of x. Our objective is to find the integral of x cosine of x dx. Again, we need to choose u and dv. We have x and cosine of x. Let's choose u equals x and dv equals cosine of x dx. Now we differentiate u to find do and integrate dv to find v. The derivative of u equals x is do equals dx. The integral of dv equals cosine of x dx is v equals sine of x. Substitute these into the integration by parts formula. The integral of u dv is equal to u times v, which is x times sine of x, minus the integral of v do, which is sine of x times d. The new integral, the integral of sine of x, is straightforward to solve. The integral of sine of x is negative cosine of x. So our expression becomes x sine of x minus negative cosine of x plus c. Simplifying this gives us our final answer. The final answer is x sine of x plus cosine of x plus c. Let's check this by differentiating. Using the product rule on x sine of x gives sine of x plus x cosine of x. The derivative of cosine of x is negative sine of x. The sine of x terms cancel out, leaving us with x cosine of x, which is our original integrand. The solution is correct. Sometimes, the integrand doesn't look like a product of two functions, but we can still use integration by parts. A classic example is the integral of the natural logarithm of x. Our objective is to find the integral of the natural logarithm of x dx. At first glance, this doesn't seem to be a product. However, we can write it as a product of 1 and ln x. We can rewrite the integral as the integral of 1 times the natural logarithm of x dx. Now we have a product. Let's choose our u and dv. We choose u equals ln x because its derivative is simpler, and dv equals 1 dx because it's easy to integrate. Differentiating u and integrating dv gives us du equals 1 over x dx and v equals x. Substitute these into the formula. The integral of u dv is equal to u times v, which is ln x times x, minus the integral of v du, which is x times 1 over x dx. Let's simplify the new integral. The x's cancel out, leaving us with the integral of 1 dx. The integral of 1 is simply x, so our final answer is x ln x minus x plus c. This is a very important result that you should be familiar with. It shows how integration by parts can be used even when the integrand doesn't appear to be a product. For some integrals, a single application of integration by parts is not enough. We need to apply the method twice. This often happens with integrals involving products of exponential and trigonometric functions. Let's find the integral of e to the power of x times sine of x. Let's choose our u and dv. For these types of integrals, the choice of u and dv doesn't matter as much, as long as you are consistent. Let's set u equals e to the power of x and dv equals sine of x dx. Differentiating u and integrating dv gives du equals e to the power of x dx and v equals negative cosine of x. Applying the formula, we get the integral is equal to negative e to the power of x cosine of x, plus the integral of e to the power of x cosine of x dx. Notice that the new integral is similar to the original one, but with cosine instead of sine. This is a sign that we need to apply integration by parts again. Let's focus on the new integral. We must be consistent with our choice of u and dv. Since we chose u as the exponential function before, we'll do it again. This gives us du equals e to the power of x dx and vi equals sine of x. Now substitute these into the formula for the second integral. The integral of e to the power of x cosine of x is equal to e to the power of x's sine of x, minus the integral of e to the power of x sine of x dx. Let's substitute this entire expression back into our original equation. Our original integral, let's call it I, is equal to negative e to the power of x cosine of x, plus the result of our second integration by parts. Look closely at the equation. The integral we are trying to solve, I, appears on both sides of the equation. This is the key to solving it. We can rewrite this as I equals negative e to the power of x cosine of x plus e to the power of x sine of x minus I. Now we can solve for I algebraically. Add I to both sides. This gives us 2i equals e to the power of x sine of x minus e to the power of x cosine of x. Finally, divide by 2 to find I. The integral I is equal to 1/2 e to the power of x times the quantity sine of x minus cosine of x plus c. This technique of solving for the integral itself is a common and important strategy for these types of problems. Let's work through one more example that requires two applications of integration by parts. This time, we'll integrate a polynomial multiplied by a trigonometric function. Our objective is to find the integral of x squared sine of x dx. For integrals of the form x to the n times a trig or exponential function, we typically choose u to be the polynomial term because its derivative simplifies with each step. So, for our first application, we'll set u equals x squared and dv equals sine of x dx. Differentiating u and integrating dv gives du equals 2x dE and v equals negative cosine of x. Applying the formula, The integral is equal to negative x squared cosine of x plus the integral of 2x cosine of x dx. The new integral, the integral of x cosine of x, is simpler than the original, but it still requires integration by parts. This is the same integral we solved in example 2. Let's perform the second application of integration by parts on this new integral. This gives us du equals dex and v equals sine of x. Applying the formula to the second integral, the integral of x cosine of x is equal to x sine of x minus the integral of sine of x d. We know the integral of sine of x is negative cosine of x. So the second integral evaluates to x sine of x plus cosine of x. Now we substitute this result back into our expression from the first application. The original integral is equal to negative x squared cosine of x plus 2 times the quantity x sine of x plus cosine of x plus c. Finally, we distribute the 2 to get our final answer. The final answer is negative x squared cosine of x plus 2x sine of x plus 2 cosine of x plus c. Let's quickly recap what we've learned. We started by deriving the integration by parts formula from the product rule of differentiation. The formula is the integral of u dv equals uv minus the integral of v d. We saw that the key to success is choosing the parts u and dv wisely. A good strategy is to choose dv as the part that is easy to integrate, and u as the part that simplifies when differentiated. We also learned that for some integrals, like those involving products of exponentials and trigonometric functions, we need to apply the formula twice and then solve for the integral algebraically. You are now equipped to tackle a wide range of integrals using this powerful technique. Practice is essential to master this method. To help you solidify your understanding, here are 5 practice questions in the style of the IBAAHL exam. Pause the video, work through them, and then resume to see the fully worked solutions. Here are the questions. Take your time to solve them. Welcome back. Let's go through the solutions. For the first question, we need to find the integral of xe to the power of 3x. We choose u equals x and dv equals e to the power of 3x dx. This gives us du equals dx and v equals 1/3 e to the power of 3x. Applying the formula, we get 1/3 xe to the power of 3x minus the integral of 1/3 e to the power of 3x dx. Integrating the remaining term gives us 1/9 e to the power of 3x. So the final answer is 1/3 xe to the power of 3x minus 1/9 e to the power of 3x plus c. Next, let's solve the integral of x squared ln. We choose u equals ln x and dv equals x squared dx. This gives us du equals 1 over x dx and v equals 1/3 x cubed. Applying the formula, we get 1/3 x cubed ln x minus the integral of 1/3 x cubed times 1 over x dx. This simplifies to 1/3 x cubed ln x minus 1/3 times the integral of x squared dx. Integrating x squared gives 1/3 x cubed. So the final answer is 1/3 x cubed ln x minus 1/9 x cubed plus c. For the third question, we need to find the integral of arctan x. We write this as 1 times arctan k. We choose u equals arctan x and dv equals dx. This gives us du equals 1 over 1 plus x squared dx and v equals x. Applying the formula, we get x arctan x minus the integral of x over 1 plus x squared dx. The new integral can be solved with a simple substitution. Let w equals 1 plus x squared, so dw equals 2x dx. The integral becomes 1/2 the integral of 1 over w bit, which is 1/2 ln of the absolute value of y. Substituting back, the final answer is x arctan x minus 1/2 ln of 1 plus x squared plus c. Now for the fourth question, the integral of e to the power of negative 2x times cosine of x. Let's call the integral I. For the first application, we choose u equals e to the power of negative 2x and dv equals cosine of x dx. This gives du equals negative 2e to the power of negative 2x dx and v equals sine of x. So I equals e to the power of negative 2x sine of x minus the integral of sine of x times negative 2e to the power of negative 2x dx. This simplifies to I equals e to the power of negative 2x sine of x plus 2 times the integral of e to the power of negative 2x sine of x dx. For the second application, we integrate e to the power of negative 2x sine of x. We choose u equals e to the power of negative 2x and dv equals sine of x dx. This gives do equals negative 2e to the power of negative 2x dx and v equals negative cosine of x. The second integral is negative e to the power of negative 2x cosine of x minus the integral of negative cosine of x times negative 2e to the power of negative 2x dx. This simplifies to negative e to the power of negative 2x cosine of x minus 2 times the integral of e to the power of negative 2x cosine of x dx. Notice this is negative 2i. Substituting back into our equation for I, we get I equals e to the power of negative 2x sine of x plus 2 times the quantity negative e to the power of negative 2x cosine of x minus 2i. This simplifies to I equals e to the power of negative 2x sine of x minus 2e to the power of negative 2x cosine of x minus 4i. Adding 4i to both sides gives 5i equals e to the power of negative 2x times the quantity sine of x minus 2 cosine of x. Finally, dividing by 5, we get the answer 1/5 e to the power of negative 2x times sine of x minus 2 cosine of x plus c. For our final question, we'll find the integral of x secant squared of x. We choose u equals x and dv equals secant squared of x dx. This gives do equals dx and dv equals tangent of x. Applying the formula, we get x tangent of x minus the integral of tangent of x dx. The integral of tangent of x is a standard result, which is negative ln of the absolute value of cosine of x. Substituting this back, we get x tangent of x minus negative ln of the absolute value of cosine of x plus c. Simplifying, the final answer is x tangent of x plus ln of the absolute value of cosine of x plus c. That concludes our exploration of integration by parts. We've covered the derivation, application, and strategies for solving various types of integrals, including those requiring multiple steps. Remember, the key is to practice. Work through the examples again and try the practice questions on your own. The more you apply the formula, the more intuitive the process will become. Thank you for watching, and good luck with your IB studies.